Hello, it's Greg and Gaijin. We're back. We hope you're having a happy day wherever you're watching this video content from. As always, we'd like to thank you for your continued support of Greg and Gaijin social media and writing efforts. Thank you, thank you, thank you. Welcome back. Today we are stepping back from our normal Japanese food, social media, and writing content found often on Craig Huffman 11 on X, and thank you for your support there. We wrote a theoretical physics paper recently. It's dense and mathematically rigorous. We thought this would be a nice bridge in a 30 question kind of Zoom lecture-esque kind of format for people who are interested in such things like we are. Doesn't mean we have every answer. Most of this, again, as a speculative paper, is not provable now in the short term or perhaps ever, but we do believe that it could spark more discussion and perhaps further research, which would make us super, super, super happy. These are quick hit and such questions. Let's get to it. Hexagonal micro-wormhole lattices, emergent time, forward consistent paths, and the microstructure of spacetime. That's the title if you're interested in finding it. 1. What's your paper about? Imagine spacetime not as smooth, but made of tiny connected wormholes forming hexagonal lattice. Each node is like a discrete moment, and time emerges as you move through these nodes. The lattice also allows multiple forward consistent paths, letting many futures coexist without breaking causality. A major novelty and a step away from mainstream theory at this point. 2. Why choose a hexagonal lattice? Hexagons are efficient and symmetric. They connect nicely with 6 neighbors, which maximizes connectivity. You see the same efficiency in honeycombs and graphenes. That's the material often used in superconcrete. This symmetry helps the lattice stay stable and makes the structure isotropic. Again, whether that's the actual shape in practice is not verifiable. 3. How does the lattice create time? Time isn't a continuous flow here. It comes from moving along the nodes. Each step is a new quote-unquote moment, so time is emergent, another key feature of this idea, from the lattice itself rather than being fundamental backdrop. 4. What are forward consistent paths? I mentioned that in the paper. These are paths that move forward without causing paradoxes. You can have multiple possible futures like branching timelines, but none allow you to loop backward and violate causality, which of course is the crux of any sci-fi movie, such as Back to the Future. 5. How does this connect to general relativity? Even though the lattice is discrete, nodes can redistribute curvature, mimicking space-time bending. Large-scale behavior can approximate smooth space-times, so it's not completely disconnected from Einstein's ideas. And I put Einstein-like, I believe, in the paper, so I don't presume to make a direct connection to his theories. Great that they are, but there is some relationship, to be sure, that I tried to show in the paper through mathematical formulas as well as research. 6. Can lattice work in 3D or higher dimensions? Yes. We can extend it to it using space-filling polyhedra, like truncated octahedra or 4D equivalents. This maintains isotropy and causal connectivity and opens connections to theories like string theory, which is of course popular, everybody knows that, and Kaluza-Klein models, which a layperson can do more research on the internet or on Wikipedia for. 7. How do you study lattice stability? Important, right? Otherwise, the universe falls apart. We can use eigenvalue and spectral analysis of adjacency and Laplacian matrices. I mentioned that a bit in the paper, including curvature feedback. These tools will tell us how the lattice reacts to perturbations and under what conditions it remains stable. Of course, such research would require more math and a supercomputer to verify, if it were verifiable at all, which I do not presume. 8. Why include micro-wormholes? Another novel feature of my idea. They provide tiny shortcuts between nodes, allowing non-local connections without violating causality. That's important. This supports multiple forward consistent paths and helps information propagate across the lattice. So I think the connections, the small level, allows information to freely flow forward, which again, on the macro level, makes the universe that we are now currently apparently living in. Again, verifiable, hard to say. In the moment, no. Short term, probably not. Long term, you never know with the advancements in supercomputers and AI. 9. What's the quantum connection? Each node can act like a quantum system with entanglements. That's a popular thing you see all the time these days along paths. Studying this helps us to see how space-time structure might be linked to quantum information. And again, some of this hopefully has some application in the future to a supercomputer, even the era of time. 10. What are the computational challenges? Yeah. Simulating large lattices is tricky. You have to track paths, node redistribution, and curvature dynamics. Difficult. It gets combinatorially complex quickly. So do the words in this lecture. So efficient, algorithm and probabilistic methods are essential. Difficult. One sentence, difficult at the current level of even supercomputers. Can the lattice self-heal? Yeah, I talk a little bit in there about black holes, and I mentioned in some of my research, maybe I didn't include in the paper, about white holes too, where disturbances in the space-time have to be accounted for. Yes, nodes adjust connections and redistribute curvature after disturbances. This self-correcting behavior allows the lattice or keeps the lattice stable, even if part of it is knocked out temporarily. And in a small tangent here, where the honeycomb falls apart in certain areas, the whole thing does not collapse, and it gives the bees times to remake it and continue on its way. So small errors, quote unquote, in the space-time aren't necessarily out of the ordinary and aren't catastrophic to this system. 12. Does this model allow for a multiverse? Conceptually, yes, which is difficult. Multiple forward consistent paths can represent alternative futures, almost like branching timelines that coexist without paradoxes. Basically, in an infinite universe, every choice is possible and freely made, but once you make certain choices, other choices are closed off, especially the backwards stuff. Can't do that, sorry. 13. How does curvature feedback work? Nodes sense local curvature and adjust their connections to minimize instability. This feedback keeps the lattice geometrically coherent over time. So small adjustments at the micro level keep the macro level, again, from falling completely apart. 14. Could we detect this experimentally? Direct detection unlikely, as I have said, at the Planck scales, the really small level, but there might be indirect signatures, for example, tiny deviations in particle motion, subtle gravitational wave effects, or correlation in quantum entanglements that could hint at the lattice. So possible, but not likely, especially in the current theoretical physics climate, unfortunately, for theories like mine and other people who work really hard to try to figure out the nature of the universe. 15. How is this different from causal set theory? Yeah, causal sets are discrete size space-time, like moment by moment, that are kind of finite, but in the hexagonal lattice emphasize structure, connectivity, and emergent time, a key feature of this theory, and self-stabilizing dynamics. It holds itself together rather than just ordering events. So it's a continual adjustment on a micro level to keep the macro level smooth. In my opinion, again, provable, difficult to say. You're going to hear me say that a lot. I don't presume to prove any of this, but it's out there, and supercomputers and other really super smart people might be able to find a path forward. That would be great. 16. How does it relate to spin networks or loop quantum gravity? The lattice complements them. It does. Spin networks focus on discrete geometry, and the lattice adds dynamic paths, curvature feedback, and multi-universe-like possibilities, giving a different angle on quantum space-time. Again, another novel, quote-unquote, feature of my paper. So there's that. I tried to break away from mainstream theories you might expect, as one should. 17. How is causality preserved? By design. Connections only allow forward traversal. Even if there are many paths, the network prevents loops that would let you go back in time. So no, you're not going to end up in a Back to the Future alternative universe and see your mom and dad. Not going to happen in this idea. 18. What changes in higher dimensions? Yeah, this is especially discussed a bit further in Appendix B in the paper. Higher dimensions mean more neighbors, increasing connectivity, and the number of forward consistent paths. Proper polyhedral tilting is key to avoiding the causal conflicts. I talk a little bit about that, and again, that would take more research, and I'd need more simulations. I put a few ideas that how that might be accomplished in the paper, but again, that's way above my pay grade. 19. Can it integrate with standard physics models? I tried to keep this really connected to what was out there. I don't want to step completely out to lunch because nobody respects that. But I want it to be unique. Yes, it can be compatible with ER equals EMR. That's a theory you can look up there with Einstein related things, frameworks, string theory, which is popular, and discrete quantum gravity approaches. And I do put some research and some other readings that one could dig deeper as they flesh out the viability of this idea, acting as a bridge between discrete space-time ideas and existing physics. So possible, possible. But again, that's an intentional effort on my part to branch out slightly, but not completely, from mainstream theoretical physical or physics models, rather. 20. How does entropy behave here? Entropy can be tracked along forward consistent paths, measuring disorder in a node states, plural, or quantum correlations. This ties directly to the arrow of time. So it should be measurable how that all fleshes out across the universe. But again, difficult to prove with any certainty. 21. Are there emergent patterns in simulations? Simulations show self-healing, path clustering, probabilistic multiverses-like behaviors, demonstrating how global order can emerge from simple local rules. So again, the micro level order leading to macro level consistency and coherence and connectivity. 22. Why not use squares or triangles? Yeah, I was thinking of a shape. What shape should I use, right? Hexagons are optimal. Squares and triangles create directional biases or even uneven connectivity, which could destabilize emergent time or cause anisotropy. Big words today. Sorry. Basically, I thought about soap bubbles and water droplets that look round, but only because of surface tension. And in the paper, I mentioned temporal tension, where some forces unknown shape the micro-wormholes from the stable hexagonal original thing. Again, whether that shape is legitimate, I don't know. Hard to say. Not provable, of course, but that's the connection. And I put that in the paper where the bubble, soap bubbles to the water bubble. I don't think I mentioned water bubbles, soap bubbles, where the roundness is from a temporal tension. That's kind of a not completely out to lunch idea. There are other theories with the foam holding the universe together, so you can do more research on that. Can the lattice collapse? Uh-oh, yeah. Extreme local perturbations can create instability, but feedback and redistribution usually restore stability, making the lattice robust under realistic conditions. So probably parts of it could fall completely apart. Hopefully not where we are, but as a whole, in this model, it would be unlikely due to its tight construction and hexagonal nature. 24. How does information propagate or change? Quantum information flows along forward consistent paths, as I've talked about. This shows a deep link between space-time geometry, the hexagonal nature, and the flow of information, potentially explaining why causality and locality emerge. Again, that would take a lot more research. I'm not going to do that in 39 pages or so. 25. Could this explain the arrow of time? Yes. Possible. Probable. I don't know. And I make no statements to claim that I have. Because transversal, or it is transversal rather, always forward along nose, a natural direction emerges. Time's arrow is built into the lattice itself. We go this way and not back. But we can go this way and we can come back, but we're still going forward. That's the idea. 26. What's the lattice scale? The natural scale is plankton, the small, extremely small stuff, where smooth space-time breaks down. That's trouble, right? And at large scales, it appears continuous, which we apparently are living in. 27. Could this affect particle physics? Indirectly, maybe. Maybe. Tiny deviations in trajectories or correlations could impact precision instruments, giving hints about Planck scale structure, the super small stuff. Difficult to... The harder you try to measure that stuff, the more energy it takes. It's a weird thing in the universe. 28. How speculative is this? It's a speculative theoretical physics paper. It's speculative, but mathematically structured. Intentionally so, on my part. It's a playground to explore links between discrete spacetime, quantum mechanics, and emergent time. In other words, I wanted to research and read and put my ideas and try to have them meet at some point logically between fantasy and reality, theory and practical application. Whether I accomplished that, I have no idea, but that was the goal. What are the next research steps? 29. Focus on stability analysis, higher dimensional lattices. Simulations would be key here. Quantum information studies, phenomenology, and integration with broader quantum gravity frameworks. Each could deepen our understanding of discrete space-time. In a nutshell, if a supercomputer could take these ideas and flesh them out, that would be great. If other members of the theoretical physics community would take interest in the idea and flesh it out, especially with more rigorous mathematics, well beyond my pay grade, who knows? 30, last question. How would you explain this to someone without physics background? Think of space-time as a giant honeycomb of tiny wormholes. Moving along them creates time, allows many possible futures, and gives space-time a rich, discrete structure that could eventually help unify quantum mechanics and gravity. I made some other really nice shorts on Craig Hoffman 11, highlighting aspects of this in a really visual format. Take time to look at those. The paper is also posted there. I appreciate everyone who took the time to listen to this kind of lecture. It helps me think more deeply as I move forward in thought with these ideas. But that's it. And as always, have a great, great day.